Hi, and welcome to our NTN webinar series. Today we will focus on NR-NTN R&D testing of chipsets and upcoming devices, as well as end-to-end testbeds, which are popular among research centers and satellite operators. In previous webinars, already we discussed at length about NTN technology in general and NB-NTN testing of chipsets and devices. However, in this session we will cover the current state of the NTN market, its use cases, challenges, and our testing solutions. My colleague team will demonstrate device testing using the CMX500 NR-NTN mobile radio tester. Then we will follow with our special guest Obi from Viavi Solutions, which will showcase an NR-NTN end-to-end testbed solution. And finally, my colleague Nassif will introduce our novel software tool for creating custom constellation test plans with our channel emulation capability using our signal generators and spectrum analyzers, which is also possible to create an OTA environment with that solution. So let's get started. So we have different implementations of NTN when it comes to device aspects. So as you know, on the market, we have 3GPP versus proprietary solutions and deployments. So the market was triggered actually by proprietary NTN solutions, started by Apple and Global Star initiative, providing emergency services. Also in the same time, or even before that, Huawei, together with their Tiangtong and Thuraya satellites, they also enabled emergency services over their GEO satellites. And also Qualcomm Iridium also announced a service in similar time. However, due to the market momentum, Qualcomm announced, of course, that this service is not requested, especially by the OEM of their chipsets. So this was discontinued, and basically what we saw it was the proliferation of 3GPP NB-NTN solutions. Started with MediaTek as the first chipset on a very first device. At that time, it was Bullet, and the first operator that we have even today is Skylo, providing NB-NTN services over Viasat and EchoStar backbones. Soon after that, we had a plethora of chipsets, and the whole ecosystem followed with the NB-NTN support of 3GPP release 17. And of course, soon after, we saw the Iridium and the Global Star initiatives on NB-NTN announcements together with different LEO and GEO constellations supporting the 3GPP ecosystem. The third pillar that we have in the NTN device aspects implementation of such services is what we call the 3GPP unmodified, or the direct-to-device or handset. And here, Starlink is the leader together with T-Mobile, followed by AST SpaceMobile with collaborations by AT&T and Verizon. And of course, we soon will see Amazon Kuiper playing a role here, but what we see from the market perspective is that a lot of these initiatives are also coming from different regions of the world. So if you see, direct-to-device is mainly dominated by US, but also we have initiative on standardized NR-NTN LEO constellations like the IRIS² by the European Union. And then we have something in between proprietary and standard constellations such as StarNet coming out of China. So when it comes to the NTN current market development, when it's come to 3GPP, we can make this distinction between NB-NTN, GSO and NGSO, or GEO or LEO, and then we can do the same distinction on NR-NTN. And of course, these different implementations have, depending on the state of the constellation, they have continuous coverage or discontinuous coverage. So when it comes to sub-6 GHz market deployment, here we have OQ Technologies being the one that has the first LEO capability that will continue to be with discontinuous coverage by 26, and hopefully onwards they will have commercial capability with continuous coverage. Skylo being the first on the market over GEO, and they're the first actually commercially available fully global solution with continuous coverage. We see Satellite IoT coming as a LEO NB-NTN constellation that will be followed by Global Star and Iridium as announced. And then what we see also things that are not announced, like the first NR-NTN sub-6 GHz LEO constellation that soon might be announced by any of the frequency asset holders globally. So we see that mission starting somewhere in 26 and then really creating a commercial service somewhere in 27. And then after that, the expectation on the market is that we will see the second LEO constellation as well. What we see at the same time, the NTN-KA and KU band constellations will happen. The 3GPP ones will happen in the same time frame as the NR-NTN at LEO, in the LEO constellations. In sub-6 gigahertz. So here we see the first NR-NTN capability over K and KU band appearing over GEOs or existing GEO infrastructure and satellite operators. Then we will see the second following around 27, and then we will see one of the existing LEO constellations or a future LEO constellation also supporting KA and KU band. But of course, in parallel, and that's what we see from an NTN market, is that the legacy technologies like DVB S2X and such offerings for such terminals will continue to exist in the offering of the satellite operators. Basically, the NR-NTN will be an added, or even together with the NB-NTN, will be an added feature set for the satellite operators. What does that mean? That means that the satellite operators, at least the existing ones, will try to create a multi-orbit offering between LEOs, MEOs, and GEOs. And that offering will also consist of different multi-band type of services for different type of terminals and use cases. So on one side, we have the sub-6 gigahertz, which is more about handheld scenarios. And then we have the KA and KU band, which is more about VSAT terminals, like in automotive and fixed wireless access type of scenarios. So when it comes to the UE development status, where we are, so first of all, currently we are at a stage where NB-NTN is released for IoT modules, and there we have at least around 6 to 7 chipsets already announced with multiple devices, IoT devices supported. So we see the major IoT module vendors supporting NB-NTN. But this first started over GEO. Now what we see that this solution, it's going from NB-NTN IoT modules, it goes for in an integrated type of solution on chipsets, meaning it will go into smartphone, wearables, and automotive. And most probably there will be the inclusion of one-way voice capability as well. As I presented in the previous slide, we will also see the proliferation of LEO capability over this NB-NTN technology. So NBN technology, what we see on the market, it's becoming a mass market technology. And in here, our solution basically is what we have already released, which is the CMW 500, where it can be used in R&D, but also it can be used in conformance testing. So here we have a very strong solution and unique on the market, where we have been able to activate all the work items in GCF for protocol testing, for RF and RRM. We were the first to activate those, but also very importantly, we were among the first ones to support the Skylo test plan. And I'm happy to say that currently we support fully phase 3 of the Skylo test plan with more than 281 test cases out of 284 test cases. So that's a very complete solution. Now, when it comes to NR-NTN, as we see the market, that will take some time on the chipset side. So where we are, we're more in early R&D, end-to-end test beds, understanding the technology, the services that can go on top, and what are the limitations. So there are a lot of POC, what we call a POC phase as well. And in a similar fashion, we see happening for NR-NTN at KA and KU band for so-called, let's say, FR3 terminals in NR-NTN. So in here, of course, Tim will talk more, but we have our CMX500 supporting all the R&D value chain within the chipset and device customers, where we have a very unique positioning because we are multi-band, multi-orbit capable with channel emulation included in a single box instrument. And of course, for all these early R&D test beds, also at satellite operators that they want to understand more the NTN technology on their existing GEO infrastructures or LEO satellites, whether they can send effectively, let's say, NR-NTN waveform over their current transponders. There we have an end-to-end test bed that we invested in the last 1.5 years in collaboration with Viavi, this is a unique and complete solution for satellite operators and for chipset and device vendors that basically has the lowest footprint on the market because the channel emulation is included into the CMX, so only 2 boxes in a way are effectively enough to create such a testbed. And then when it comes to this direct-to-device services, where the actual effect of the Doppler and let's say the Doppler frequency is being compensated instead of the UE, it's more compensated by the constellation. What SpaceX or Starlink and AST Space Mobile and Link does. In such scenarios, but not limited to those, we do offer our channel emulation capability with robot arm for OTA environments to test, for example, also phased array antennas, the beamformer capabilities, etc. More of this will be covered later on by my colleague Nassif. Yeah, so when it comes to our test solution for NTN, we provide test solutions across the entire value chain. So as you see from left to right, we support satellite access node testing with our spectrum analyzer and signal generator. Here, R&D centers can do 3GPP waveform verification, for example, on transponders, or they can do 3GPP conformance for base stations, regulatory, and as well they can use it in production. Then we have our UE testing tools, such as CMW500 for NB-NTN, and then we have our CMX500 for NR-NTN testing. And of course, in the same manner, we provide R&D, early R&D and production R&D test tools and for the value chain. Also, 3GPP conformance, NetOps solution, and regulatory as well as production. And last but not least, we also do the end-to-end system emulation for NTN test beds, where we have the UE emulation, as I mentioned before, done via Viavi. And with the CMX500, we have our G-Node B emulation. However, also we have channel emulation capability using our FSW, SMW. So in that sense, customers, prospect customers like research centers, universities, thinking of 6G research or NTN in 6G, they can create such demonstrators or end-to-end demonstrators capable of SL, KA, KU bands and in both GEO and LEO orbits. And in terms of field testing, of course, here we have our scanners and Qualipox solution, where for live networks, customers could actually do coverage testing. In this part of the webinar now, we will transition more into the deep dive of our main product, which is CMX500. It is the heart of our NR-NTN offering, especially when it comes to UE testing. And here now I would like to hand over to my colleague Tim to tell us all about the CMX500.
Yeah, thanks Goetze for all the market information you provided. Very interesting what is currently happening here. Well, Goetze already mentioned the CMX500 is a device where we can simulate multi-orbit and multi-band satellite networks. That means that we can test and analyze signals from, for example, LEO, MEO, GEO, and also GSO satellites, all in one box. We support different kind of frequency bands, including L and S band. For the L and S band, we use the RF unit to deploy that. Then we have the IF unit, which is used for the KU band. And if you want to go to the KA band, then we also add our remote radio head. And then you have really the ability to test all these bands. There are possibilities to also, of course, do mobility scenarios like a handover, for example, from terrestrial to non-terrestrial, or also from a non-terrestrial to a non-terrestrial cell. All these kind of mobility scenarios are a key role when it comes to NR-NTN testing. We have our interactive web GUI, CM Squares, where we visualize all the relevant data. For example, the elevation, the Doppler, the delay, and we also have a nice satellite view. I will show you later some of these elements. Protocol testing is very important here because protocol testing is like the early stage when it comes to NR-NTN testing. We provide some XLAPI Python scripts which can be used for protocol testing to verify whether the general protocol messages are properly working. Measurement, of course, we have the typical AlexBrayer measurement or also TX multi-eval here. And the last point we always want to point out here, application testing. Application testing, especially in the context with NR-NTN, is very important because at the end of the day, it is important to verify whether, for example, streaming, gaming, maybe in the future also XR applications are properly and smoothly running via the NR-NTN network. And for that, we have the data application unit, which provides the possibility to connect the CMX, for example, to a company network that you can directly access to a backend service from your company, or also to the internet that you can really do live internet access streaming, for example. We are able to set up to 6 satellites at the same time with full channel emulation on the CMX, all in one single box. So we talked now about the CMX 500, but we want to go one step further. Yeah, so for example, when it comes to customers like satellite operators, right? So they are like, okay, I have big constellations at the end. I want to deal with how do I do that at the end of the day? For that case, we are introducing a new tool, our satellite constellation tool. It's an application where you can define the position of the UE and use it as a reference point. You can load predefined constellations, for example, from Starlink or OneWeb, but you can also load your own constellation in it based on TLE file. You can select the corresponding satellites, right, which are currently visible from the UE. And with this selected satellites, you can then deploy this kind of sub-network on the CMX directly. And that makes it very easy, for example, to analyze NTN coverage issues. So, for example, you have files from the past, right? And you want to know, why did I not have any network at that time? So you can load in the TLE files, and then you can replay the scenario and see where there were some issues. At the end, also important is to observe the behavior of the satellite constellation, over the time, for example, how things are changing at the end of the day. So this is a tool we will provide. It plays together with our CMX 500 and the NR-NTN functionality. Basically, it's an export of the settings you defined in the tool, and then you can just replay that on the CMX. I will also show you that later in a demo. So the last topic I want to cover is conformance testing. So there is a time also where conformance testing is getting very, very relevant in that environment. For that, we have our conformance system as already known. And we are looking very closely to this Run 5 progress at the moment, what is currently happening. We have already our first PCT test cases available. And of course, also RF tests are already available here. So now I want to show you a demo of both the CMX user interface with our web GUI for the NR-NTN functionality and also our satellite configuration tool. Okay, I want to show you now a typical handover scenario, which is a crucial aspect of satellite communication networks. Let's take a look on how we set up and configure our network for that use case. We start by creating a network with 2 NR cells, so a standalone network, on our CMX 500 in a network emulation. This is a key step in establishing our NTN network at the end of the day, because we need to flag these NR cells we just created as NTN cells, which unlocks our NTN-specific parameter configuration, which includes, for example, like ephemeris type, which allows us to select the correct orbit format, or also downlink, uplink, polarization, and also, of course, the predefined NTN constellations for select our target orbit to ensure the seamless communication. In the future, this is very important to know, is that we also offer custom profiles based on TLE information. So it's not that you are linked to these predefined orbits. You can also load your own orbit constellation directly in the CMX. Now we have our NTN cells set up. So let's enable our NTN cells and prepare the network configuration for the handover. We'll then attach the NTN cell with the higher power to the network. So you can see here this purple square will pop up. So that means we have an active connection from the UE to this specific cell. And then we can initiate a handover by going to the mobility and saying handover. Now you can see that the purple changed from the cell we were just connected to the other cell. That means the handover took place. Okay. So now we are basically interested in to do some measurements at the end of the day, right? So what kind of measurements can we do here? We can do, for example, RX blur measurement, right? So to see, to evaluate basically the performance of the NTN network. So we can see here now the blur. And of course, also, I want to show you what we changed in the GUI in general regarding to visualization. Yeah, so this is also important. We saw now we can perform mobility, we see where the active connection is currently happening, but also important, what about the graphs to visualize what is currently going on in the communication, in the connection at the end of the day. So for that case, we updated our CM Squares web GUI with new squares, with new graphs. And one of these key enhancements is that, for example, we added new squares for elevation, for Doppler, or also our total timing advance, the delay at the end of the day. And you can see that here now, for example. And this provides a very clear overview of the NTN cells and making it easier also to monitor and manage your network. With CMX Mars, we have a full log analysis support on the device, on the CMX500. In here, you can see the ZIP19 message being broadcasted with all the ephemeris data. And also from follow-up protocol messages, we can see how the UE is successfully reached. And also a PDN connectivity is established. When it comes to handover, you can also observe those, like in this case, where the UE took around 200 milliseconds from RRC reconfig to complete. This gives you a comprehensive understanding of our satellite network's performance and status, everything in one web GUI. Yeah, I already mentioned the satellite constellation tool, which we just introduced, and I want to show it to you now. So you can see here on the left top side, we have the settings UE location, where you can select basically a predefined UE location. And this location is also visible here on the right side as this button. What you can also do, for example, you can also use your own longitude and latitude. You just copy it in and then it's automatically adjusted also on the satellite view on the right side. In addition, when it comes to the constellations, we also offer some predefined constellations. For example, I can select here now Global Star or also Starlink. Yeah, and you can see how the satellite view here also changes corresponding what constellation I select. And then I can also use my own satellite constellation input, for example, by using this TLE format. Yeah, so you can just copy paste your TLE content here, and then it will also visualize on the right side in the satellite view. In addition, you can, for example, also set up the duration for how long this should be visualized, so the satellite path, and also the visibility limit from the elevation angle. So the interesting part here is now basically when you selected, for example, something like OneWeb, right? So we are here in Munich. We can see now the visible satellites on the right side. They are colored here in orange. Yeah, so from the position where we are with our UE. Let's say I want to pick out some of these satellites because what I want to do, I want to have this typical scenario. I have my UE, I'm somewhere, I'm connected to the terrestrial network, and at some point I want to have this handover from terrestrial network to a non-terrestrial network. Then I continue, stay in the non-terrestrial networks, and then at some point I go down again to the terrestrial environment. Yeah, so for that reason, we could select, for example, some of the satellites. Yeah. So you can see here in the satellite selection on the left side, we basically show you for all the satellites which are available in constellation, we show the visibility. So we can select now some of these satellites, and you can also see here now in this top orange line, the summarized visibility based on the satellites we selected. So of course we have currently 100%, and then we can select some more, and then you can also see how this graph automatically adjusts here, right? So let's say I select, for example, 4 satellites. And what I can do now, I can export this selected satellites to the CMX and use that for as network deployment at the end of the day, right? And then I can do this mobility testing. Yeah, I already showed it on the CM squares. We can then do a handover from terrestrial to the non-terrestrial network or cell, and then we can continue depending what is deployed in the network. So in addition to this visualization and the settings, what we have here, when we take a look on the right side of the tool, we have a very nice view about visible satellites. So here over the time, over these 300 seconds, for example, which is currently set up here. Yeah. So this is something we set up on the left side of the constellation selection. We see over the time which satellite is visible at which time. Yeah, and when I go here over my cursor, I see, oh, okay, at some point the one satellite is becoming, for example, invisible, like we can see here at the end, and at one time another satellite is coming visible. Yeah, so this really helps you to get an overview or to see very easily like what is the coverage of a specific satellite. Yeah, so for example, if I would do this with satellites which are not having such a good cover, you can see how the picture automatically adapts, yeah, which is also a very interesting testing point or testing aspect at the end of the day. In addition to that, to this satellite visibility, we also visualize the fading information, so the corresponding fading data for all satellites. Yeah, so we have here the Doppler, the elevation, the Doppler rate, path loss also, altitude, yeah, and also the propagation delay. So all this is available as a web application, so it's very easy to access it. And yeah, it just helps you to really replay these typical scenarios which are happening in this NTN environment. Well, I just showed you the latest updates on NR-NTN development regarding the CMX500, including also our new tool, our satellite constellation tool, which enables new possibilities when it comes to, for example, visualizing and also setting up a corresponding NTN network for the CMX500. Gotze, back to you.
Thank you, Tim, for this comprehensive overview of the CMX500. So, continuing with our webinar, as I presented earlier, our NR-NTN solution portfolio, we continue to the end-to-end system emulation capability. So here we have with me Obi from Viavi Solutions, basically to introduce and to talk about our mutual testbed that we have been working on for the past 1.5 years. So maybe from this point forward, Obi, tell us more about this testbed, what it consists of.
Cool. Thank you very much, Gotze, for the opportunity today to come to your studio to present the end-to-end testbed which we've been working on. And thank you for the very warm introduction. So we're going to talk about the end-to-end testbed that we've been working with Rohde & Schwarz for the past 1.5 years. Working with the TM500 and the CMX together to create a system that provides lots of benefits to people that want to evaluate, want to test, and want to deploy NTN scenarios. So the TM500, starting there, is a UE emulator, in fact, the leading UE emulator in the market, and has been emulating 3GPP UEs all the way from 3G, 4G, 5G now, and now NTN. So working with Rohde & Schwarz, we came together to build this testbed where the UE is connected to the base station emulator, which includes the full channel capabilities that Tim was talking about, as well as a network, full 5GC network included in the box. So with the TM500 and the CMX, the smallest footprint on the market, we can emulate a full NTN end-to-end system. So let me introduce some of the key benefits of this testbed. So we can cover a lot of scenarios with it, including TN as well as NTN scenarios. And also we have an unmatched diversity of emulation scenarios, such as NTN to TN handovers, TN to TN handovers, and a lot of other scenarios that Tim also mentioned in his presentation that just went by. So we also cover all the different orbits from LEO, GEO, and MEO. And this way, it's seamless in the sense that the UE, TM500, has the ability to set any location you want on Earth. So when you set that location, in addition to the SIB19 ephemeris data, we can model any constellation or any satellite height that is desired. Also, we're going to say that this is very compact. With just the TM500 and the CMX, you get the full end-to-end capabilities without the need for extra devices like independent channel emulators in between the two devices. And finally, what you get with two of the leading providers of this type of RF equipment is that you get expertise from both teams, and both teams are at your service to make sure your goals are achieved when you look into using this testbed. So now I'm going to go through a few scenarios that you can set up with these systems. Granted that we're showing just one of each, but really the imagination on what situation or scenario you want to set up is really up to you. So what I'm showing now on the slide is two TM500s coupled with two CMXs, all linked up to a data network in the middle, as well as a device from Viavi that creates real data applications. In this way, you can do truly end-to-end data, starting from one UE on the TM500 on the left-hand side, all the way through the network, through the channels, and down to the other UE on the TM500 on the right-hand side. So one example of a test bed that we can create using these devices, as I'm showing on the slide, is a true end-to-end system from the application layer of one UE all the way to the application layer of another UE. So you can see here, the TM500 on the left will be generating data that will flow through the first CMX, through a data network, onto the second CMX, and onto the second TM500 on the right. This way you can evaluate the performance of your data applications from one end all the way to the other end. What you can also do is be flexible with the type of links that you have between the TM500 and the CMX. From the first TM500 CMX, you could have an NTN link, which could, as we said before, either be LEO, MEO, or GEO. And on the other side, you could have a terrestrial link, which could be FR1 or FR2. And finally, if you do not want to use the RDA from the TM500, the real data application device here, you can also connect your own specific custom data application directly into the TM500. And that way you can use that to evaluate custom data types that haven't even been invented yet. So you can use this for effective research into the appropriate data types that can be transmitted effectively over an NTN link. Going to the second option that we have, we see this as a way to test in a lab more research-like activities. So what we have done here is to pair a couple of CMXs with a single TM500, and that way you could have a UE or a couple of UEs in TM500 connect to two independent networks. So one could be a PLMN in one country, and the other one could emulate a PLMN in another country, fully and effectively end-to-end. And this way, you could also test things like handovers. You could also test mobility scenarios. So a UE moving within one cell. So you can cover a lot of scenarios here with this type of thing. So TN to NTN, NTN to NTN, and TN to TN as well. The TM500 also supports LTE all the way from release 8 up to release 16. So you can also use that to emulate LTE on one of the cells of the TM500 if needed. So, and then the third option which we have is where you can use the TM500 and the CMX deployed over a real satellite to evaluate your satellite's performance. So we have seen that this is the case where on the market now, as Goche said earlier, we don't have full NR-NTN chipsets, and NR-NTN GNOBs commercially are not yet available. So with this type of setup, a satellite operator could use a release 17 and in fact release 18 TM500 UE coupled with a CMX GNOB emulator and test the data end-to-end over their individual satellite links. So we see that as a very effective way of evaluating especially the transparent NTN mode where the satellites have already been deployed. So as a summary of the use cases, I like to make it classify them as evaluate, test, and deploy. So evaluate is where you evaluate in the lab, that end-to-end system I showed, and you can do your data analysis on your custom data applications. You have your test one, where you're trying to generate new ideas in the lab, research labs. You can use the TM500 and the CMX to evaluate new concepts in mobility, new concepts in handovers between terrestrial and non-terrestrial. And then finally, in deploy, you have a deployed satellite. You can use both the TM500 and the CMX to deploy and to test an already deployed satellite. So now with the summary of the capabilities of this testbed and what I've explained, I'll hand back over to Goche for any questions that he may have.
Thank you, Obi. Yeah, as we were involved in this mutual testbed, which I do believe has a lot of advantages as we see in running projects with satellite operators that have existing GEO satellites, for example, or even the ones with LEO. So what would be a typical test bed in a live scenario, right? So we have on one side like a live GEO existing satellite, as you said. So we do connect our CMX500 on an existing gateway or ground station. And then your TM500 gets connected to?
So the TM500 will get connected to, especially as you mentioned, a GEO satellite, to a RF device, such as a VSAT or a parabolic antenna that can transmit to that specific GEO satellite.
Exactly.
So you see the architecture will be the TM500 on one side on the ground, connected via a VSAT to a satellite. The satellite beams back down to the gateway, as you've mentioned, and connected to the CMX. That way you get a full end-to-end setup to be able to do your evaluation of that satellite.
Yeah, so basically customers, in this case, satellite operators specifically, can verify NR-NTN capability, waveform, including signaling.
Correct.
Of a UE all the way down to the ground station and emulated G-Node B, and how that basically existing GEO infrastructure can carry NR-NTN,
exactly.
preparing them for the actual 3GPP deployments and entering 3GPP ecosystem into the satellite operator world.
Yes.
Yeah.
And as we've mentioned before, the TM500 can be connected to a data source, which is independent. So it could even be a data source from the internet. And if you also mentioned, the CMX could be connected to a data source, which is also connected to the internet. So you could even go all the way from internet to internet
exactly.
via a GEO satellite.
Yeah, very good. Thank you. Thank you, Obi, for visiting us and doing this webinar with us. Thank you. It was a pleasure.
No problem. Thank you for having me.
Continuing with our webinar, we have our next solution as part of the end-to-end system emulation. And here we will be talking more about our channel emulation and OTA capability for NR-NTN or NTN in general type of simulation. Yeah, so in here with me, I have my colleague Nassif. Nassif, welcome to the webinar. So we will be talking next about part of our end-to-end emulation capability, which is satellite channel emulation and OTA environment, right? So effectively, if we see this end-to-end, let's say the test bed where we have, for example, KU band or FR3 NR-NTN UE to be tested with an antenna, phased array antenna and a beamformer capability. This is where we see the importance of an OTA environment being needed, but also the ability to emulate feeder and service link, right? So maybe tell us more about our capability and tools that we can address this.
Of course. Thank you, Gotze, for the introduction. So it's my pleasure to introduce our satellite channel emulation solution. Obviously, we can do both the feeder link as well as the service link channel emulation. But for this presentation, maybe I go in the direction of the service link because I think it shows the full capability of what we can do in terms of channel emulation, as well as I get to explain the unique satellite trajectory flyby emulation that we do with this robotic arm. So I think this is the path we're going to go. The core of this entire process is based on this software. So this custom software that we developed in order to basically make all these things happen. It's called the Space Nexus. And it is divided in two sections. The upper section is for taking the input, so to say. So one is we import satellite constellation information. And then we also get to plug in our UE mobility information, such as we can emulate static UEs at any location in the world. We can emulate or put in information for movement, such as speed, direction, and we can even import waypoint files. So if it's navigational data of the UE, we can also plug it in. So from these two inputs, what we do is then we can derive two sets of output. One is for the fading profile. So that's the data that we need to do this channel emulation, RF channel emulation. And then the second output is for the robotic arm in order to emulate this, different satellite trajectories for emulating flybys. Now let's look into the software steps in more detail. So it's divided in 4 steps. The first step is where we import the constellation file. Now you can import any constellation file. In fact, we have developed some download tools that you can use to retrieve TLE information in real time from the NORAD database. Here you have the 2D and 3D visualization for Starlink, OneWeb, and Globalstar's constellation. So this is the entire constellation. We use the SGP4 model to break down this TLE information. So then we know the exact position of that individual satellite or any individual satellite in that constellation file. And we can also calculate the future projected locations of those satellites. In the next step, what we do is we define the UE's location, mobility, all that kind of information. So here, for this concrete example, what I did was plugged in, instead of Starlink and on all the constellation you saw, here's a constellation of the 2 experimental satellites from Amazon Kuiper, and plugged in the UE location in Orlando, Florida, right? And then we check for visibility. So right away, you can see that we have visibility with Kuiper's 2 satellite for a total duration of 3.5 minutes. This means this is the animation that we can also do with our tool. So basically what happens is this 3.5 minutes is when the UE can establish a communication link with the Kuiper satellite. And after this 3.5 minutes, the satellite is gonna go out of range. So this is basically the time which is very critical for us. So we figured this out. Now we move on to step 3. In step 3 is where all the technical calculations take place. Firstly, we have this 2 information that we plugged in, the satellite constellation and the UE information. Now what we are going to do is we're going to convert this to ECF format coordinate system, which is the Earth Center Fixed coordinate system. And then we also plug in a few more information about the link, frequency, the condition, so the environmental condition and the spatial condition of the UE, right? And once we have all this information, we can do some orbital geometric calculation to figure out 3 parameters that are very important for the channel emulation. So the first one is path loss. Then we have the Doppler shift, and then the latency, one-way signal delay, right? And as you can see that these are all moving or updating. That means that as the satellite is moving away or firstly coming towards the UE and then moving away, so this information is continuously being updated, and we are also doing the same. Now, in the next step, within this calculation bit, we also send this fading profile into our vector signal generator. So let me explain. So this is going to be a little bit more concrete. We're going towards an example. So here is our GNB, right? The CMX. The downlink RF is being sent into the spectrum analyzer. We then down convert this RF information to digital IQ. We then send this digital IQ to the signal generator, where we modify the IQ signal on the fly with this fading profile that we just calculated. And then we send it out to the antenna that is mounted on the robotic arm. And then we basically make a connection with the UE. On the uplink, it goes straight to the RF port of the base station. So this is one concrete example for DTC. So direct to device testing, right? So here's another example where we did Starlink's DTC satellite testing. So Starlink is using LTE, so we replaced the CMX with our LTE call box, the CMW. but the working principle is the same. So RF goes into the spectrum analyzer, down converted to digital IQ, goes into the signal generator where we add the fading information, send it out through the antenna, and then the uplink goes straight to the base station. And you can see here that the fading profile is completely zero. So the UE is basically seeing a terrestrial base station, but it's from space, so the path loss and the signal delay is a bit more than normal terrestrial base station. And you can see that there's a drop in power level when the fading profile is switched on, right? We can still get a connection and pretty decent throughput values, as you can see. So we also simulate the satellite motion for this satellite as well. And I will show you in the next slide what that looks like. So all in all, this is proof that this kind of communication really works from this DTC satellite, which is amazing. So here is the second part, or the second output we talked about. So step 4 in our process, where we move the cobot arm. So the antenna is mounted here, as you can see, and it is slowly moving. So this whole scenario, so this visibility with this DTC satellite was for 2 minutes. Roughly 2 minutes. I think it was 2 minutes, 22 seconds, a bit more, right? So this will, over this 2 minutes, slowly move that entire trajectory that was defined. So since we have done this ECF conversion, so we leverage that, and then we convert that into a Cartesian coordinate system, so XYZ basically. There's one benefit of this. So we can, once we do this conversion, we can basically replicate those different angles, because the satellite does not always fly over the UE. Like it will obviously, depending on the location of the UE, will have certain angle with that satellite flyby trajectory and the UE position. And it is very important when we test, let's say, beamforming modules and those kind of phased array to have those precise angles replicated in our mimic version of the satellite, movements. And we can do this to a very good accuracy. So the current uncertainty is around 0.09%. Which is like 1 millimeter if we come down to this scaled down version of the satellite flyby. So really, really accurate system. We tested it quite a lot, and then we're very excited about this solution, to be honest. So with that, I think I have come to an end to my presentation. I hope you learned something useful out of this. So without much waiting, I hand over to my colleague Gotze.
Thank you, Nassif, for this great overview of our OTA testing capability and channel emulation on NTN. With this, we're coming to an end of our webinar, and I hope we have provided you with useful information on how you can do R&D testing in chipset and devices, as well as how you can do end-to-end testbed verification, whether you're a satellite operator, research center, or a device manufacturer. So with that, I would like to close this webinar session. Thank you.